Okay, this is going to be our sixth and final video in our series on magnetic fields and magnetic forces. There's just a couple of topics that I wanted to talk about. There's not a whole lot of calculation to do in these two sections, so we'll kind of get right into it. I'm just going to talk about a couple of topics that are in these sections that are important for us. So section 27.8 talks about DC motors. So I'm only going to show you guys a diagram here of how a DC motor works. We'll talk a little bit about that, and then we're going to move on to the Hall effect. The Hall effect, really there's only one equation that we're going to want to work with. I'm going to talk a little bit about it, and then we'll do one example using the Hall effect. Okay? So let's get into it here. This video is going to cover, as I said, everything that we're interested in from sections 27.8 and 27.9. So starting off with 27.8, we have DC motors. We kind of want to have an idea of how these work a little bit. So these are very simplified versions of well, all these are one motor just in different states, and this is a very simplified version of how this would work. Okay, so let's take a look at the diagram here. What do we have? We have permanent magnets here. We have the north pole of some magnet over here. We can imagine this would be connected to a larger magnet, or maybe this whole thing is some C-shaped magnet or something, and this is the south pole of a magnet. Okay. Obviously, they don't exist on their own, right? Is all I'm saying. They're parts of larger magnets. So we have these two magnets, these two permanent magnets set up, and then we have this coil of wire, this sort of again C-shaped coil of wire set up, and it's connected to a power supply here, to our source, with let's say the positive terminal on this side and the negative terminal on this side, setting up a current that when these brushes are in contact with these little C-shaped connectors here, that we have a current running around the loop like this. Okay, so we have this set up to start off with, and because we have current running around the loop, we could use the right hand rule, sort of point our thumb downward and our fingers curl around the loop in the direction of the current. We can see our magnetic dipole moment points downward, right? And so if we have a magnetic field, as we would from these two permanent magnets, pointing from the north pole to the south pole in the direction of our B vector here, well, we're going to end up with a torque that points in this direction, and this is going to cause our current loop to want to rotate in a counterclockwise direction, right? So this thing starts to rotate in a counterclockwise direction, and eventually we get to the point where this sort of reddish pinkish section of the loop ends up at the bottom, and the oh, one second, let me just pause this. Sorry about that. Right, so we have the coil has now rotated, and we have the pink portion sort of pointing downward, and the blue portion on the upward side here. But as this thing rotates through the brushes here, we can see here that there's a little bit of a gap, right? So now we're at the point where nothing is making any contact, so there's no more current flowing through this part of the loop, and so we no longer have a magnetic dipole moment, and so we no longer have a torque, and so this thing kind of just continues to rotate because it was initially rotating, right? So we had sort of accelerated the rotation with the torque, right? And we could sort of get more formal about how all this works with angular accelerations and so forth, but the idea is that we would still have some angular velocity here. This thing would still be rotating, and then it rotates to the point where now the blue side is in contact with this brush, and so the current starts to run up the blue side and back along the pink side, right? And so it rotates to the sort of third setup here, when it goes all the way around 180 degrees, and now we see the current is heading up the blue side and back down the pink side, right, which is the opposite of what we had here. It sets up the same magnetic dipole moment, which gives us the same torque, which gives us this rotation in a counterclockwise direction, and so we end up with this section of our motor here spinning faster and faster, right? And this is basically a simple version of how all of these DC motors are going to work. Now there's going to be points where we're going to be having a lot less torque on this thing as we have less of the magnetic dipole moment pointing sort of perpendicular to our magnetic field. But you can imagine that you could build up the strength of this thing, the load that it can spin up, by just adding in more loops, by offsetting them slightly, so that you always have a really favorable angle between your magnetic dipole moment and your magnetic field. And these things can become able to move pretty large loads, right? And so this is just a really simple sort of overview of how these DC motors would work. And that's really all I wanted to talk about from section 27.8. Let's move on now to section 27.9, where we talk about the Hall effect. And it's a fairly interesting effect, so we're going to look at it a little bit here, and we'll do one example with it. So we're going to take a closer look at charge moving in a conductor, and this conductor is in a magnetic field. We want to look at a conductor in the shape of a flat strip now. So this sort of rectangular area that we're looking at, we can imagine that it is a sort of flat strip conductor. Our current is moving in the direction of our positive x-axis here, so we can see our current density pointing in this direction here. We have a magnetic field that's pointing in the positive y direction. And then we have two sort of separate cases here. We have the case of a negative charge moving with drift velocity to the left here, and this would again correspond to a current moving in the positive x direction, because we have negative charge moving in the negative x direction, right? So that corresponds to a current in the positive x direction. Or, as we have in diagram B here, we have positive charge actually moving with drift velocity vd in the positive x direction, again corresponding to our positive charge density here, moving in the direction of the positive x axis. Okay, so far we've only talked about really the current moving through here, but what's sort of happening? Excuse me. What's sort of happening as this current is moving? In both cases we have, so I kind of wish I could have this paragraph and the diagram on screen, but maybe maybe we can have kind of just the bottom one on screen here. So in both cases we have this moving charge, but the magnetic field is driving the charge, or maybe I'll just go back to diagrams. The magnetic field is driving the charge up to the top sort of edge of our conductor in both cases, right? Because our VD, when we look at VD and our magnetic field, we can see that there's going to be a net force upward on both of these charges, because they're moving in opposite directions and they have opposite charges, so both of them are going to be driven upward. So what sort of ends up happening is we end up with a buildup of either positive charge on the top edge of our plate here, or negative. I guess it would be negative here, or positive in this case. So the moving charge is what gets driven upward. We end up with a buildup of that charge on the top edge of the plate, and a corresponding buildup of the opposite charge on the bottom plate, right? Because we have charge conservation across the whole conductor. And so depending on which sort of charge we have moving, we start setting up this electric field, right? There's going to be negative charge in this case on the top plate, or the top edge of this plate, and positive charge on the bottom edge of this plate. And so we set up an electric field in this direction, right? And we have to remember that this again is a negative charge. And in this case we set up an electric field pointing in this direction, but this is a positive charge. And so because of this whole setup, and because of the force experienced by the negative and positive charge, we end up having this sort of situation. Once we have enough charge built up, we enter this steady state where the force experienced by the moving charge due to the magnetic field, which would normally be upward, is then balanced out by the force experienced by this charge due to the electrostatic field that we have set up here, right? And so you enter this steady state where there's no longer any more charge being built up, and your current just flows through the wire or the slab or whatever you want to think of this thing as, right? And so this kind of sets up rather quickly, but one interesting effect of this is that we end up having a potential difference between the top and bottom of our slab here, right? There's going to be a potential difference because we have charge building up on the top and bottom. This potential difference is what we call the Hall voltage, okay? And the polarity, or the which side is at higher potential versus which side is at lower potential, is completely dependent on what type of charge was moving. Do you have negative charge moving, which is corresponding to the current running through your conductor, or do you have positive charge moving, right? So if we do experiments like this on different conducting materials, we find that metals in general actually do have negative charge moving. So it's actually electrons moving in the opposite direction of what we think of as the direction of our current density, right? And if we look at other materials, sometimes we're going to see that it's positive charge moving in that direction. And so the positive charge is a little more complicated. I'm not going to go into it here. It really turns out to be sort of lack of negative charge that's moving. It's sort of holes in positions that could contain negative charges are often what's moving, but that's more technical than we need to get into, so we don't really need to sort of worry about that. The key takeaway here is that there is a Hall voltage across these strips of conductor, and the polarity, or the direction in which we have this potential drop is dictated by whether we have positive or negative charge moving, right? And in the case of metals, it's negative charge moving. Okay, so in the steady state, when we have charge running for a little while, when we have our current running for a little while, and charge has sort of accumulated on the top and the bottom of this tab, we end up having this sort of balance between our electrostatic and our magnetic forces. So we have no net force anymore on the charges moving through. We can kind of clean this up and end up with this expression that we see here. Okay. If we then remember the work that we did in chapter 25, where we're talking about how we can write down our current density, we can kind of write it down in this way, right? We have our current density is equal to the concentration of mobile charge carriers times the charge of those carriers times our drift velocity. These are vectors. But we can then write down the sort of scalar version of this equation as you see here. And if we combine this equation with this equation here, we can generate this expression here, which is what is called the Hall effect. Okay, so let's take a look at what the Hall effect is telling us. It's telling us that the concentration of mobile charge carriers, N, times the charge per carrier is going to be equal to the negative of our current density times our magnetic field divided by our electrostatic field in our conductor. Okay, and so each of these has their sort of direction by the way it's sort of drawn on the diagram up here. Okay, so this is another useful equation that we're going to want to have. This will get added to the formula sheet at some point, and so we can do an example sort of using this equation. That'll demonstrate how we could use it and how some of the important information we can kind of pull out of it would be acquired here. So this is example 27.12 from the text. This is a Hall effect measurement. And so what do we have going on here? We place a strip of copper which is 2 millimeters thick and 1.5 centimeters wide in front of or into a uniform 0.4 Tesla magnetic field. This is exactly the setup that we saw above. I won't bother scrolling up again. You can kind of take a look at it. It's just that slab sitting in the magnetic field. We then run a 75 amp current in the direction of the positive x-axis through this slab. Then we see that the potential at the bottom of the slab is 0.81 times 10 to the negative 6 volts excuse me, higher than it is at the top. Okay, so from this measurement we want to determine the concentration of mobile electrons in the copper. Okay, so how would we do this? Well, we want the concentration of mobile electrons. The concentration of mobile electrons is the concentration of charge carriers. So we want N, and we know that NQ is equal to minus JX BY over EZ. Okay, that's just the Hall effect. So we can obviously quickly rearrange this. We can end up with N is equal to minus JX BY over Q EZ. Okay, and so now from the information that we're given, can we calculate everything on the right hand side of this? Well, we can. We know that JX, our current density, is just going to be our current over the area of our conducting slab, right? So we can do that calculation very quickly. We're going to have 75, which is our current. This is 75 amps over the area of our conducting slab. Well, we have its thickness and its width, so we can do that calculation. 2 times 10 to the negative 3, 1.5 times 10 to the negative 2. Sorry. Should be an equal sign there, and if you do this calculation, you find 2.5 times 10 to the 6 amps per meter squared. Okay, so that's our current density in the x direction. Can we do anything about our electric field? We can do something about our electric field. We know that our electric field in the z direction is simply going to be the potential difference across our slab in the z direction times the distance, right? We know that the electric field can be measured in volts per meter. So our EZ is simply going to be V over D, which is just going to be our 0.81 times 10 to the negative 6. That's going to be in volts, but I won't put the units in there. And then we have a distance of centimeters across this thing, right? So we're going to end up with 1.5 times 10 to the minus 2 meters, right? So if you do this calculation, you're going to end up with this value here. Have it over here. What is it? 5.4 times 10 to the minus 5 volts per meter. Okay, so we have our JX, we have our EZ. We know we're given the strength of the magnetic field, and it's all in the y direction, so that's our BY. Q is just the charge on an electron, so we can just look that up and sub that in, and so we end up with the expression. We're going to sub it into this expression here. We end up with N is equal to minus 2.5 times 10 to the 6. That's our JX from here, times our magnetic field, the magnitude of our magnetic field from the problem, divided by the charge on electron. This would be in coulombs, but we won't have the units, and times our electric field. Okay, like that. And so if we do this calculation, we're going to end up finding that N is equal to 11.6 times 10 to the 28, and this is going to come in at meters cubed. Well, 1 over meters cubed, right? So this is really the number of charge carriers, the number of, I guess you would think of it as free electrons in a chunk of copper that would be 1 cubic meter, right? That's what we ended up calculating. This is a density of these charge carriers per some unit volume, and we're talking about a unit volume that's a cubic meter, right? So this is the value that we get from the Hall effect. The actual value for copper, so N is actually equal to, for copper, is equal to 8.5 times 10 to the 28 1 over meters cubed. Okay, so same units obviously, but the difference here is small. It's only sort of off by maybe a factor of I don't know, 1/3 or something. Anyway, so you can see that they're relatively similar, but the difference between these two values is because the Hall effect is sort of a simplified version of what you would really need to do this calculation. To be able to do the full detailed calculation like this, you would have to be able to include quantum effects again, which are not really within the scope of this course. But we can see that the Hall effect, which is a relatively simple expression that we can calculate already, gives us a pretty good approximation, only off by a few percent from the actual value for the number of charge carriers in our copper per unit volume, right? Okay, so that was sort of the end of the end of section 27.9, and really the end of chapter 27. So we'll leave it here, and I will see you guys in the next chapter.